Now, if you've ever worked with Pwn College or exploit development, you probably worked with some of these tools. Uh, you have your more manual tools like Ghidra and GDB and WinDBG for Windows, and then also the more automated tools like AFL and Anger. Now, these are good tools to work with, and I enjoy working with them. But when it comes to, whether it's personal projects or whether you work in exploit development, there's always room for optimization and improving your efficiency. And the most popular, I guess, method of optimization and improving efficiency is through AI. Now, AI is very controversial when it comes to certain fields, especially software development. But I think that the reason that there's two sides to it. I guess people either believe that AI is just it's great, it's going to take over, and it's going to replace the jobs of software developers. The reason that they think that is because there is so much training data, and really, when it comes to software development, it is kind of it's a very, I guess you could say, algorithmic field. There is only, think of any idea you have, whether that's creating some kind of service or an app on like a system app, whether it's like related to movies or like shopping or like e-commerce or logistics. Those all kind of fundamentally have the same architectures in terms of like the low-level programming that like a junior dev will do to the higher level system design, the distributed system design that a senior developer would do. And because all of that exists, people post their designs and code on GitHub, and these large AI companies can train with it. Obviously, some companies feel the need to not even bother hiring people anymore. They just use AI for this. Like some companies will just use AI to replace junior level roles. But I know with companies like Anthropic, they claim that AI is doing a lot of the coding, which is obvious by the way their whole business is going. And the other side of the opinion when it comes to AI is that it's not really good enough to replace developers. Now, obviously, that isn't true completely. When it comes to certain roles, like it is very likely that junior roles for software development will be replaced, mostly just due to the fact what a junior dev does. You can reliably replicate whatever work they would do with artificial intelligence. But when it comes to like the higher level, thinking about synchronization, preventing race conditions, when it comes to like individual parts of your large-scale system, that AI may struggle more with that. Now, when you really think about what an AI does, or machine learning or whatever, or large language model, it's essentially just very fancy pattern recognition. All those chatbot agents like ChatGPT and the code generators slash agents like Claude, they learn all of that through patterns. And if we think about what we do in system security, it's a lot of pattern recognition. Whether it be source code review, or fuzzing, or manually looking at how the program runs in memory with GDB, or how it's being compiled with Ghidra. When you look for potential vulnerabilities, you're looking essentially for patterns. Now, for example, like if you were reviewing source code, you would look at the fact that, okay, this user doesn't use like a mutex or a semaphore when they access this resource. This is potentially a way we can exploit this program via some kind of race condition exploit, like replacing the file in the time that it's accessed by another process. Now, because of this heavy, I would say that despite the fact that system security is very pattern heavy, it's not as much as something like software development. And also, system design is a lot more, I guess, I would say unique in the sense that when you become a software developer, you're kind of expected to program a certain way. There are safety standards, efficiency, People are obsessed with like the whole leak code being efficient, which sometimes leads to decreased security in your actual code, if you don't implement it correctly. But systems system security is a lot more. It has patterns, but you have to understand the what you're working with, which could be the Linux ecosystem or whatever it is, or some kind of embedded device. You have to understand it very well, most likely better than an AI would be able to understand it, because again, an AI, it doesn't know something. It it learns the ability to predict what comes next in certain words, so it doesn't really understand what like a Linux system is. It could tell you like, oh, Linux like memory management, like it could tell you what a heap, whatever you want to call it, a dynamic allocator is. It just doesn't really know what it is. To write some kind of vulnerability, you have to know what it is, because okay, if I do this, this causes this, and this causes this, and the whole thing. Like, I'm sure you've seen how complex T-cache vulnerability exploits can be. Now, for the side of people that believe AI, is kind of junk when it comes to technical work, there is proof that it is currently being used. Like at the time of writing this, about a week and a half ago or a week ago, Google released a document saying that there's this 0 day that came into their crosshairs, and after analyzing it, they come to the conclusion that it was most likely AI was used to write the 0 day. They don't say that like it was completely written by some kind of AI agent, but it did aid this group of I guess you want to call them system security researchers, although I think it was a malicious context, but it aided them, and that's kind of what I'm proposing, or not really proposing, but what I'm hoping to change your mind on, because I know a lot of tech people are against AI. So yeah, it's just like some proof that it can be used for our specific, very niche field. Now, a big skeptic, a few points of skepticism is, okay, if you look at software engineering, because of how well these artificial intelligence agents can replicate like junior level stuff, the bar of entry is raised. If you ever tried to prepare for an SWE interview, you got to learn system design, Python, hopefully, if that's what the role needs, but most of the time it's like JavaScript. But then you're going to do the actual like coding interview in another language. You have to know about like software development patterns and life cycles. You have to know algorithms and data structures very well, even though most higher level software engineers say that they never really used it on the job. It's really just kind of a way to weed out less desirable applicants. Essentially, like if you compare the bar now to like 20 years ago, it's clearly a lot higher. But with a system security, these companies, like whether you're going to go into like academic stuff, like working with a PhD research, or go into these government contractors like Battelle or Mantech or whatever, when it comes to my experience with the government researchers, when I applied to a few of them, their bar of entry is really just, because this is such a niche field, you have to understand low-level systems. Just show us that you have a basic understanding, and then we'll teach you the rest, because this is such a specialized field. It's not like software development where, if you have experience programming e-commerce websites, you'll probably still be able to get a job with like Spotify, because it's not like the same service, but the fundamental like building blocks are the same. You have experience, how would you say this? You have experience building like large mass scale services. With vulnerability research or system security research, there are exploit primitives like memory corruption or code reuse, but when it comes to different like system architectures, different uses for these systems. Like, there's embedded servers, normal personal computers. The targets can be different. The way you actually go about exploiting a system can be different. Even at the architectural level, there's the microarchitectural exploits like Spectre, and like obviously that would be a lot more useful to a company like Intel than it would for a company like how like Battelle. They focus on general nonprofit research, but obviously Intel would be a lot more interested in like a Spectre-like exploit. So the point is saying that even AI is very unlikely to be able to specialize in all of these fields, because again, it doesn't really understand it. And then another thing is that this field is, because it's so niche, it's not very popular, really. Despite that, there's a large demand. Like you see in the bottom right, I put the Reddit user counts for the general programming subreddit, which is, I'm sure if you've ever wanted to be a programmer, the first thing you would do is go to the programming Reddit, even though that's not really it's not very helpful. Like you'd be better off going to like a specific back-end developer subreddit or whatever. But the programming gets 297,000 weekly visitors and 4.2 thousand weekly contributors. If you compare that to the exploit development, and this was the most popular one. Like I also looked at the malware analysis subreddit, the system security, exploit development, of course, and a few other ones, and this was the most popular. And you can see that there's only 4.9 thousand weekly visitors and 100 weekly contributors. So it's a very niche field, and that also goes into like job market and the likeliness of being replaced, because it's so niche. There's not really a lot of training data. And because every exploit dev has their own way of doing things, they work with the basic primitives, but it's not like system security where you're expected. It's not like software development where you have your patterns that go from the low level to the high. Like at every level there's a pattern that you must follow to be like a hireable, desirable developer. With system security, you have your exploit primitives, and then you also have your background knowledge in systems. But from there, to actually like be very good at it, you have to understand your specific niche very, very well. If you look into the heap exploitation stuff, there are those different houses. I forgot the name of the houses exactly. They have their background knowledge on the dynamic allocator. They have their background knowledge on systems, but for their specific type of vulnerability that they exploit, they have to understand it very well. It's very unlikely that AI is going to understand this very niche field at a point where it just replaces us completely. I feel like if that ever happens, then most jobs would probably be replaced by then, because there are a lot more popular jobs. By the time system security exploit dev stuff is replaceable, then there probably isn't going to be very many jobs regardless. Same with the job market. But the ability to aid existing researchers, that it's very high. It's essentially like having a partner that can state, essentially, it's kind of like a coding agent, but it doesn't write your code for you, because AI can't really replicate. Like you can't just tell AI make an exploit for me. It can't do that, but it can do, like, it can help you with creating Ghidra scripts, any kind of bash script for some automation pipeline, help you understand certain concepts, because if you've ever looked at like C, like the man pages on Linux for C and Linux syscalls, they're really long, they're really disorganized, and they're not very beginner friendly, and even if you aren't a beginner, they're still really hard to read. If you've ever read the Windows API documents, they're very abstract. They just kind of assume that you've read like 100 other pages and just know what this is talking about. When I've done malware analyses of like a WannaCry or the Zeus Trojan, I did use ChatGPT to like help me understand what is this Windows API document even like trying to say to me. Okay, so this system call does this. Okay, so I see why it's now being used in this piece of malware. Now, the big thing is, how do we train our agents? There are two existing datasets. One called Juliet, And just like to briefly explain what that is it's essentially a data set of a bunch of C files, and these C files are labeled. So if you've worked with ML, you know that you have to label your data set such that the agent understands, like, okay, this is wrong, this is right, so let me learn from that. Okay, and essentially it's a bunch of C++ files with different functions, and some of them are they're quote-unquote safe, although older versions of this data set do have mislabelings, I guess if you want to call it, and bad functions, which are explicitly stated to like have like a buffer overflow, use after free vulnerability. It's a big collection of C files, and all of them, and it covers a lot of the CWEs, like I said, buffer overflows, etc. And you use this to train your machine learning model to detect vulnerabilities in C code, which is helpful. But if you ever really like looked at vulnerability research when you're doing like source code audits compared to systems level stuff, when you're debugging the program and then looking at decompilations of it to understand how it's really working with like P code or whatever, it's not really the same. And on top of that, for proprietary software, you don't always have access to the source code. You have access to like an executable, but not really the source code. And on top of that as well, when you go through the process of like compilation, using different flags for optimization, or different library, or I forgot the exact name of it, when you declare specific libraries that you want to import on C in the header file, like POSIX and whatever. When you do that, you lose a lot of the original semantics and potential leaks, potential areas of interest for exploit developers, because and then on top of that, you have to consider like the architecture that it's being compiled on. You lose a lot of that semantics, relationships between data, as well as, again, potential areas of interest for exploit devs. Now the ROMEO dataset is kind of a more broad application of the Juliet dataset. So I said that the Juliet dataset works with C, but the ROMEO dataset is essentially the same dataset, but they cleaned it up and generated created this pipeline that helps you turn the Juliet dataset into an x86 dataset. So you're working with object files, not source code files, and this is a lot better, I would say, because again, when you compile, you lose a lot of semantics, you lose a lot of potential areas of interest, and again, you're not always given access to the source code. Why wouldn't the best way to look for vulnerability be in the thing you're working on, the actual executable that you're working on? You're not going to, your computer isn't going to be running the source code file. The source code file is essentially just instructions, I guess. So is the object files, but the C code is just kind of like a blueprint, but you have to still compile it and then have certain optimizations and then have certain architectures. The ROMEO dataset gets closer to what the chip is actually running, which is assembly. Okay, now these are just two datasets that you can think of when it comes to training your machine learning model to detect vulnerabilities on executables. Now, to go into actually how the ROMEO dataset works, you start off, here's just like an example Juliet source code file. It tells you specifically where the flaw is, and it uses the suffix bad to indicate whether a function is good or bad. And it's worth noting that the vulnerability can actually span multiple functions, and they do take care of that in the ROMEO pipeline. So it's just like an example of a Juliet source file. Now again, the Juliet source file dataset does include a makefile, and what the researchers that worked on the ROMEO dataset found was that it's actually better to manually compile it, assemble it, and then link it, because by doing that you actually leave more more semantics, more important context than you would than just automating it. So that's what they did. Rather than like just having it become an exe file, they actually went through the process of compiling it, assembling it, and linking it to create a .o file, or an object file, depending on whether you use Windows or Linux. Now, given these disassemblies, they're just working with like pure assembly now. Now they do have to actually process it a bit before they can start tokenizing it and normalizing it. The first thing is, okay, you have this big chunk, like this big dump of assembly. How do you actually know where a function starts? There are labels, but they do specifically say that they want to exclude labels to prevent information leakage, which could help the agent rather than having it learn itself. So to indicate where a function starts, they do put it in exclamation point. And again, they do use they don't call it masking, but essentially is masking. What they do is they remove a lot of labels that would aid the agent in learning whether a function is good or bad, which is kind of how masking works if you think about it. For LSTM, I believe transformers also use it when they learn to I'm sorry, I think only transformers use it when they learn to predict the next sequence, the next token in a sequence. That's kind of what they're doing here, but not exactly. Another thing is that a lot of, well, as I said before, a lot of vulnerabilities actually span multiple functions. So they, rather than just like having a bunch of separated functions, they essentially just kind of merge it together to become one large function, and then they can look at the actual the patterns that arise from that. And lastly, they label their functions as good or bad. I did see that they removed the original labels. That's kind of because a lot of the original labels do cause data leaks. These labels are more so just for the machine, for the model to learn, okay, good or bad. That's really it. The other labels did leak more information that they didn't want. And okay, now that they've pre-processed this data, they go through the process of splitting it into 8, 10, 10 percentages. Now 80% is for training, 10% is for validation, and the other 10% is for evaluation. And again, they tokenize it, normalize it, and actually start training. Now, what did they actually find? They used CodeBERT, by the way. Now they found that it actually works very well. And this is just for x86. They got high accuracies when it came to detecting whether a function was good or bad, or safe or vulnerable. But they did find actually that context, which is essentially just like functions around the target function, and not like labels, just like context of where this vulnerability is, and then what comes around it in terms of like assembly instructions. They found that context actually did improve the accuracy of the model. Without it, it got about 90.2%. With it, got 96.9%. Okay, so that was really it. I hope that this little demonstration of how we would train an AI model to even learn about exploit development in the first place, I hope that has convinced you to embrace AI for our field. Maybe software developers don't really want to embrace it, and that's valid, because it's a lot more likely to take that job. But with us, I would say that we're safer for now. By the time our jobs got taken, that'll probably be when robots rule. Thank you.